In this supplementary video, we will discuss the solution to the two leftover velocity problems in exercise 5. So the problem 15 says the following. So if the rock is thrown upwards on the planet Mars with a velocity of 10 meters per second, so its height after t seconds is given by h equals to 10t minus 1.86 times t squared. So we are asked to find the velocity of the rock after 1 second, and in general, we want to find the velocity of the rock when t equals to a. And also, we need to find out when will the rock hit the surface, and with what velocity will the rock hit the surface. Right, so let's start by figuring out part B, because once we have got the solution of part B, we plug in t equals to 1, we get a solution of part A. Okay, so we will start by setting v of t as the velocity of the rock at time t. So then v of t is going to be the limit of the difference quotient h of t plus h minus h of t divided by h. All right, so this is actually what we want to compute. Okay, plugging in the expression for h. So we see that h of t plus h is going to be 10 times t plus h minus 1.86 times t plus h squared. And h of t is going to be 10 times t plus minus 1.86 t squared. Okay, so this is a very long numerator. And let's simplify a little bit. So just expand everything. We see that there will be 10t plus 10h plus, that will be minus 1.86 times t squared plus 2th plus h squared. And finally, that will be minus 10t plus 1.86 t squared. Okay, minus 10t is gone with the first guy, and 1.86 t squared will be gone with the middle guy over here. So what remains in the numerator, let me write it down. So it will be the 10h minus 1.86 times 2th minus 1.86h squared. And then, yeah, I think that's it. So nothing else remains. And then this whole thing is over h. And now this over h can be divided in each term. So after the division, we can plug in h equals to 0 to directly compute that the limit is precisely 10 minus 1.86 times 2 times t minus 0. So the answer will be 10 minus 3.72 t. Well, the unit is going to be in meter per second. All right, so that will be the formula for the velocity. Now to answer part A, all we need to figure out is v1. So you plug in t equals to 1, you get 10 minus 3.72, and the answer will be 6.28. And the unit will be meter per second. All right, so for part B, we are looking for the velocity at the time A. So we just plug in t equals to 8, so as to get 10 minus 3.72 times 8. And that will be the answer for part B. Okay, so let's supplement the unit over here. Okay, so for part C, so note that the rock hits the surface when h of t equals to 0. So this will tell me that 10t minus 1.86 t squared. Well, if you factorize this guy, that will be 10 minus 1.86 t times t. So you need to solve the equation that this guy equals to 0. And obviously, there will be two solutions, t equals to 0 or t equals to 10 divided by 1.86. Okay, so since t equals to 0 is really the moment when the rock starts moving upwards, so that's why you should not use t equals to 0 as a solution. You should only use t equals to 10 divided by 1.86 as the solution. And either you compute it by calculators or you compute it by hand. At the end of the day, you will get the number roughly being 5.38 seconds. So the answer is the rock hits the ground, hits the surface at 10 divided by 1.86 seconds, which is roughly 5.38 seconds. All right, so that will be the answer for part C. Okay, let me move everything to the left a little bit. All right, so for part D, so all you need to do is to plug in the time when the rock hits the ground and figure out what the velocity is. So then do not plug in the 5.38 over here because that will make the computation much uglier. But instead, you plug in the fraction, you will see that it's much easier for you to compute because this is precisely 10 minus 3.72 times 10 divided by 1.86. And then you will see that these two guys cancels out and with the factor 2. So what I'm getting at is 10 minus 20. And the answer will be minus 10 meter per second. So the answer is that the rock hits the surface with velocity 10 meter per second. So because we know that the rock hits the ground with a speed downward, so we do not need to emphasize there is a negative sign over here. Yeah, but this is actually a minor detail that you don't need to worry about too much for this course. Okay, so this is the solution to number 15. So for number 17, well, just read the problems very carefully and just compute the quantities according to their definitions. All right, so the problem says the following. So the displacement of a particle in feet moves into a straight line. Well, this displacement is given by the formula s equals to 1/2 t squared minus 6t plus 23, where t is measured in seconds. So we need to first find the average velocity over each time intervals. So let's briefly recall what the average velocity is. So the average velocity over the interval AB. So this is simply going to be the displacement at the time B minus the displacement at the time A divided by B minus A. So that will be the formula we need to use for part A. Okay, so to answer each part of part A, all you need to do is to plug in A and B's. So for example, for the first part, so the average velocity we are looking for is basically s of 8 minus s of 4 divided by 8 minus 4. So that will be 1/4 times s of 8. Let's see what's s of 8. S of 8 is actually 1/2 times 64 minus 48 plus 23. So that's my s of 8. And my s of 4 is going to be 1/2 times 16 minus 24 plus 23. All right. So the first guy will simplify as 32 minus 48 plus 23, and the answer is going to be 23 minus 16. That will be positive 7. Okay, so the second guy is 8 minus 24 plus 23. So that will be 8 minus 1, and the answer will be 7. So it will be 7 minus 7 divided by 4, and the answer will be 0. So that will be the part 1. And for part 2, we need to actually figure out s of 8 minus s of 6 divided by 8 minus 6. So the denominator is 2, so this will contribute to the 1/2 factor in the front. And we have computed s of 8 in the previous step, namely it's 7, and we just need to compute s of 6. So this will be 1/2 times 36 minus 6 times 6, that will be 36, and then plus 23. All right. So that will be minus 18 plus 23, and the answer for s of 6, this is actually going to be 5. So what we are doing is 7 minus 5 divided by 2. That will be 2 divided by 2. The answer will be 1. So that will be part 2. Okay, so for part 3, we need to have s of 10 minus s of 8 divided by 10 minus 8. So the denominator is 2, so I have got 1/2 factor in the front. And we need to compute S of 10. That will be 1/2 times 100 minus 60 plus 23. That will be, so this guy is going to be equals to positive 50 minus 60. That will be minus 10. So 23 minus 10, that will be 13. Okay, so we know S of 8 before it was 7. So what I have is 13 minus 7 divided by 2. That will be 6 divided by 2. The answer will be 3. And finally, for the fourth part. We're now looking for S of 12 minus S of 8 divided by 12 minus 8. So the denominator is 4. So I have a 1/4 factor in the front. We need to compute the S of 12. So S of 12 is going to be 1/2 times 12 squared. 12 squared being 144. And 144 divided by 2, that will be 72. But let me actually leave it for the next step. Okay, so then it will be 6 times 12. 6 times 12 is precisely 72. So the first two guys actually cancels out. What remains is just the last guy, 23. So S of 12 is precisely going to give me 23. And we know S of 8 is close to 7. So that will be 23 minus 7 divided by 4. That will be 16 divided by 4, and the answer will be 4. Okay, so let me supplement the unit. So the unit is actually going to be feet per second for each one. All right, so in order to make space for part B, so I need to erase all this, and let me actually place all the informations on top. Okay, so this is what I have obtained in the previous slide. And now let's actually look at part B. So part B, we are looking for the instantaneous velocity at the time t equals to a. So let's just recall that the instantaneous velocity at the time a. So this guy is going to be equals to the limit of the average velocity where the terminal time b is approaching a. And alternatively, you could also write it as the limit of S of a plus h minus S of a divided by h as h approaches 0. Okay, so these are the two ways of computing the instantaneous velocity. And for part B, because we are looking for the instantaneous velocity at t equals to 8, so I will just use the first definition to make the computation. So the instantaneous velocity at the time 8 is going to be the limit of S of t minus S of 8 divided by t minus 8 as t approaches 8. Okay, so S of t, we know what that is. Well, by our formula, it will be 1/2 t squared minus 6t plus 23. And we have computed S of 8 in the previous slide, and the answer was 7. So that's what we have known. So then divided by t minus 8 as t approaches 8. Okay, so to simplify the fraction, let me actually get rid of this 1/2 factor, and by multiplying everywhere on top and on the bottom by a 2. So then the bottom will becomes 2 times t minus 8, and the top is going to be t squared minus 6 times 2t plus 23 minus 7. This whole thing and times 2. So that's what I'm going to get. So simplifying, I get t squared minus 12t plus 16 times 2, and the answer will be t squared minus 12t plus 32. So after the simplification, I will get the limit of 2t minus 8 in the denominator, and on the top, t squared minus 12t plus 32. And the numerator can be easily factorized as t minus 4 times t minus 8. And then together with the 2t minus 8 in the denominator, you can get rid of the common factor t minus 8. And the answer will be 1/2 times t minus 4. And as t approaches 8, so the whole thing will approach 8 minus 4 divided by 2, and the answer is going to be equals to 2. All right, so the unit is feet per second. So the answer to part B is just 2 feet per second. Okay, Now let's place all this information on the graph. So first we are asked to draw the graph of s as a function of t. So in order to do that, so notice that s can be simplified as follows. So first you factor out the 1/2 in the front. Then you have got t squared minus 12t. So I will just do the completion of the square in order to actually make it easier for me to draw. So if t squared minus 12t will be my coefficients, then I need to supplement a 36 and minus 36 inside so as to get a square. So the first three guys over here will then combine as t minus 6 squared. And the last guy is actually going to be canceled out with the outside 23 over here. 36 divided by 2, that will be minus 18. And then minus 18 plus 23, that will be positive 5. So what I'm getting at is going to be 1/2 t minus 6 squared and then plus 5. All right, so that's how I will see my graph. So the graph is basically going to be obtained from y equals to 1/2 t squared, but then shift to the right by 6 units, and then upwards by 5 units. So using this information, it's quite easy for me to draw the following graph. So that way we have got this guy is just obtained from 1/2 t squared, and then shifted to the right by 6 units, and shifted upward by 5 units. Roughly speaking, that's what I'm getting at. Okay, so the next requirement is to draw the secant lines whose slopes are the average velocities in part A. So that the secant lines that are passing through for x equals to 4 and x equals to 8. So that will simply be this guy over here. And you see that the secant line is precisely going to be horizontal and with slope 0. And this coincides with our computation that the average velocity is 0 over here. Similarly, between 6 and 8, you see that the secant line is going to have the slope. Well, at the point A, the function value is 7. So the slope of this secant line is precisely 7 minus 5 divided by 8 minus 2, and the answer is going to be equals to 1. So this will precisely be a line of slope 1. It doesn't look like a line of slope 1 because I chose the different scalings at the x-axis and y-axis over here. So yeah, but that's going to be the secant line for part 2. So similarly, you can draw the secant line between 8 and 10, and you can draw the secant line between 8 and 12. So at the end of the day, so those 4 periods will have the secant line as shown in purple over here. So that will be for part A, for part B, for part C, and for part D. Okay, so that will be the picture for this part. And finally, we need to draw the tangent line whose slope is the instantaneous velocity in part B. And then if you draw the tangent line at the point 8, you know the slope has to be equal to 2. All right, so if you draw everything up to scale, so that you actually get the following red tangent line over here. So this will be the tangent line, and the slope will be 2 for this one over here. Okay, so this concludes problem 17.